in grad school, I had a roommate who mailed a letter. It had this, he forgot to put on the stamp, it was an incomprehensible address. It came back and, said undeliverable. And so he basically put it in the mail with him and kept it coming back. And so my other roommate, how many times this letter was going to keep on, it came back like 4 or 5 times. It was the same thing. Besides me. Okay, so we did a whole bunch of things yesterday. We looked at waves in a metal. And we're going to skip a lot of steps because I'm not going to go through the whole thing. How do we start off though? Which is? Okay, because we need it today too. I need the waves we start with. Curl of the vector. Okay. So we started here, we did the curl, we had the E. Got this guy here. This guy we said it went to rho, and what did we say with rho? It's constant. We said that this is a constant. That goes to 0. Okay. This goes to minus partial b with respect to t. So we could exchange these here. Okay, what did we do with this term? So this is our mu naught j, and our j became our j free plus partial b with respect to t. And then you're going to show in homework. Homework 6. You're going to show that J free is sigma E over this 1 minus I omega over gamma. Okay. How is gamma related to B? It's reciprocal. So the factor of M. So this, I'm sorry, it is the B over M. But how is that gamma related to tau at the collision time? It's reciprocal of that. Okay. So we put all that in here and we beat on that. And what did we end up with? Oh, okay, so we put all that in here. And then that gave us a mu naught sigma 1 minus I omega over gamma. Partial E with respect to t. We got rid of all the minus signs as well. Plus, we wrote this term as 1 over c squared. Okay, we had that. Okay. And then what did we assume? We assumed the form of a plane wave. Right? We assumed, I did record this, right? Yes. Nope. I was getting nervous in that little recording thing. False. That goes away. We assumed a form of a plane. We said that this is E equals E naught, e to the I. Yeah, assume the form of E equals E naught, e to the I. So you're going to cut off my other side? Oh, I mean, yeah, move it back. Oh, I can be back? Yeah, I'm losing too much of this right here. Perfect. Yeah. It'll work. KZ minus omega t. We shouldn't write for that in here. We put this in here and we beat on it a lot. And what did we end up with? We're just going to jump to this one little expression here. We beat on this and we ended up with n squared equaling 1 minus omega p squared. Yeah, is that too much of a job? I mean, I don't mind about what's there yesterday. Okay. Okay, so I guess. Okay. So this term gives us what? Get the partial. So
I minus I omega, no, minus I omega.
Times the rest of this.
Yeah.
So when you take the time derivative here, this gives us this mu naught sigma over 1 minus I omega over gamma. Then we got a minus I omega e here for this one. This one gives us what? So that gives us
Minus omega squared.
minus omega squared c squared e. My buddy here gives me
Negative k squared.
minus k squared.
That's one.
Well, the whole thing, so if you do this right here, this really gives you the E naught, give the I, AZ minus omega. This whole thing here is okay. All the E's go out. We got rid of all the minus signs, and then we divided through.
No, we assumed omega is there. It's like
we did that for one thing. I'm going to skip that stuff.
okay.
But which you're satisfied. So this gives us the omega, this omega here, I, mu naught sigma, 1 minus I, omega gamma, plus omega squared over c squared. Does that make sense? Okay. Now, what did we do? We said we took this from over here, we multiplied the top and bottom by I think we beat on this term here for a second.
We did it before.
We took this term here and we multiplied top and bottom by, I want to say I omega here like this. Okay. So if you do that, this gives us the minus and the minus I, and this turns everything a positive. That gives me omega squared mu naught sigma over this term and this term give me a positive. So I'll write off of that term, omega squared over gamma I omega. And then we had plus the omega squared over c squared equals k squared. Then we multiplied by c squared over omega squared. We did that. The omega squareds cancel here, so this gives me c squared omega naught sigma here over this guy here. Plus this is a 1 equals c squared k squared omega squared. What did we say this term is here? That's our n squared. That's our n squared. I'm gonna then this gives us n squared equals 1 plus c squared mu naught sigma omega squared over gamma plus I omega. And we'll multiply this side through by top and bottom by gamma. And I think this is where we left off yesterday.
We got to the plasma frequency square.
Yep. So if I multiply through there, we're going to get this guy here. C squared mu naught sigma gamma omega squared plus I omega gamma. Now, stated without proof that that term here is the plasma frequency square. Now, what does the plasma frequency mean? Again, I stated this without proof. Oscillation of electrons in a box. Imagine I have a metal here. I can view this as an electron gas. there's going to be a frequency in which the electrons will go back and forth also. And that frequency is called the plasma frequency. And the claim is that it's this term. Okay. That's actually very hard to show at this stage. Okay. But then it just clapped my hands and said, it has thus been declared. Okay. Now, if you look in the little homework here, how to get a minus sign here?
Also, don't have C.
I was about to ask.
Yeah, I
which one?
What?
Yeah,
The
Did I-
word is being divided in.
Probably five.
I'm multiplied top and bottom here by the C. So you're saying, did I mess up something here?
I think that first term should have a negative from when you multiply two i's together.
Yeah.
I thought there was a minus sign.
I think that was
Yeah.
something you didn't erase.
It was just something I didn't erase.
Yeah.
Okay. So this is here, like that.
I think so.
So you're saying the C squared is actually in the bottom?
In my notes.
Okay.
Well, look at my notes. I think
Hang on.
there was a negative in the below.
I think I made a mistake then yesterday because that I think has to probably.
Don't see my notes.
Let me put Grace music a little bit there. So
Getting this the
yeah, so I had an I up there.
Yeah.
Yeah, so this one should be a minus sign here. This is correct here. That's all happy. Here. And so this actually has a C squared. That's actually wrong from yesterday. That C squared should be, yeah, the C squared should be on the top. It's actually wrong from yesterday. It should be this. Now, you can do a couple things here. I want to get rid of mu naught. Tell me how to get rid of mu naught. I mean, I can use mu naught. What does mu naught equal?
number.
4 pi times 10 to the minus 7. Excellent. Good. Okay. That's what mu naught is. I want to get rid of it. Tell me how to get rid of it. Yep.
Well, C squared would be 1 over mu naught epsilon naught.
Exactly. So I can say that I can rewrite this as 1 minus 1 over mu naught epsilon naught. This is my mu naught. Sigma gamma. Omega squared plus I omega gamma. Like that. And then they cancel. Now tell me how to get rid of epsilon naught. I'll give you a hint. I have 1 over it. I mean, I'm going to leave it like this. If I want to get rid of it, what do I do? I multiply the top and bottom here by 1 over 4 pi. Right. 1 minus 4 pi sigma gamma 4 pi epsilon naught. And then why would I do that? 1 over 4 pi epsilon naught is my buddy k. And I know what k is. It is 9 times 7. Okay. So I can rewrite this as this 1 minus. You should yell at me here, this would be the 4 pi k sigma gamma. If I wanted something a little bit easier. regardless, what we're going to do is that we're going to still rewrite this as 1 minus omega p squared over this omega squared plus I omega beta. Now we said something about gamma. We're going to assume that gamma is small. We're going to let gamma be small. And this is where we ended things yesterday. So yesterday we ended the class with n squared equals 1 minus omega p squared over omega squared. Okay? So this is where class ended yesterday. Now, we're going to look at two cases. Omega greater than omega p, and omega less than omega p. So what happens if omega is greater than omega p?
Your n squared is greater than 1.
N squared is greater than 1. Is that right? N squared
It's less than 1.
is going to be, but it's real.
Yeah.
Is greater than 0. Okay. So in other words, n is real. Okay. Because this term here is greater than this, so this is actually going to be less than 1. So this is going to be something real. Okay. What does that mean? If my wave has a frequency higher than the plasma frequency, what can't the electrons do? They can't easily respond to the electric field. The electric field is moving so fast that those electrons basically they have a finite mass. They're not going to be able to respond fast enough. So those electrons basically are staying still. So what is that wave going to do? Go right through the material. Okay? So when you have this case here, the waves are actually going to go through the metal.
So if we manage to vibrate on itself, but this frequency can be left in the wall.
Sure. Okay. The flash did it. Okay.
Yeah.
If you can't trust, comic book superheroes, who can trust? No. So this means that the waves travel through the metal. That the oscillations, waves oscillations, so fast. The electrons can't respond. Now, if you do the other case, where we're below the plasma frequency, what happens here?
Well,
Less than 0. In this case, n squared is less than 0, so n is we've seen this case, what happens when we have the imaginary n? The wave is dead. What's going to happen here is that the wave, the incident wave, will basically attenuate in the middle. Okay? And so what's going to happen? The wave is not going to get through the metal. Make sense? Why is that happening? If you're below the plasma frequency, what can that electron do? it can actually match that driving frequency. And if you have those electrons going up and down, what's going to happen? You have that damping term, and you're basically going to lose all that basically from all the collisions with the electrons with other things. You're going to lose all that energy, and that wave is going to damp out a little bit.
So the metal would just heat up a very small amount.
Or it depends on what really. Okay, that makes sense. Questions? You'd have a reflection on the surface. So, you're not going to penetrate. Questions? Now, what I did is started this last year. A lot of the engineers needed to know something about more anisotropic materials. And so the classic case is birefringent. So what I want to do is actually explain how birefringent works. This is from that book from Brigham Young called Optics. It's actually an excellent book. They got it's free. I sent you the PDF for it. If you haven't downloaded it, download it. It's actually quite excellent. It's free. It's I would argue it's easily the best optics book out there. It's sophisticated, but I think it's a good book. I'm going to follow this because basically I think it's the best description I've had. Just so you know, there's going to be a couple of things you're going to have for daily home. They're going to hurt. Okay, the results are going to be easy. I mean, the result is going to be something simple, but to actually get it, I think there will be much swearing behind my back when you're working with this assignment. And there's going to be something. And it's actually going to be, I'll give you a little bit more quick than I have. It's actually their assignments. Somewhere they say show something. And so you're going to show them. I can't remember which one it is here. I'll give you a little bit more of a push, but it's going to hurt. So before we actually talk about birefringence, I want to talk about anisotropic crystals to begin with. So let's do a little review. Let's talk about propagation. Of waves in an anisotropic medium. Okay, we're going to look at birefringence. So let's do a little review. What causes anisotropy? What was our model that we had for our crystal? Whole bunch of atoms connected by springs. So we can draw our little atoms here. There's a spring, atom, spring, 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 and so on and so forth. Then this is actually three-dimensional. So how do you make it anisotropic in this model? So you make different spring constants. So if this is y, if this is x, I can make this would be kx, 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 ky, 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 y, and then if there's a z, there would be a kz. So you just make different spring constants. And we said there's an effect here. We said that for linear material, media, we said that this P here is proportional to E. Or we said the most general, and what was the proportionality constant? Chi, and then we needed what to get the units, right? Epsilon naught to get the units, right? We said the most general one is going to be what? And the most general relation. Most general linear relation. There's going to be that, if we look at this, px is going to be basically epsilon naught chi xx, dx, plus epsilon naught,
uh,
chi xy, ey, and epsilon naught, chi xz, ez, and then likewise for py and pz. Does that make sense? And what can we do with all this? We could write it in terms of a 3 by 3 matrix. So we said we could take all that here. And I said that we could write this P and I put a 1 bar under it, and this means a column vector, Px, Py. It's going to be what? Epsilon naught, pi xx, pi xy, pi xz, writing out a space, dx, y, z, let me check. Yes, okay, and it's legible too. Okay, chi, yx, chi yy, chi z, chi x, chi y, chi z. And that's how we look. Now, this, I'm going to state this as a fact. So this is our susceptibility. That's it. Those of you in classical mechanics, you'll find out pretty soon what it means to be. Formally, what it truly means to be. I think you were doing this on. So I think you were too.
I think a little bit of it.
So we're going formally what it means to be a tensor. Doesn't really matter. This is actually turns out to be symmetric. And I'm just going to clap my hand and say it is. This is actually a symmetric. Tensor. What does that mean? It means that chi xy equals chi yx. Okay. And that chi xz equals chi zx. And that chi, one more, yz equals chi zy. Okay. Now, when you have a symmetric matrix like that, you can always switch, you can always rotate your coordinate axes to make this diagonal. And I'm just going to clap my hands and state that this is true. And for those of you in classical mechanics, it will be true. So, math truth, or let's say math theorem. Whenever you have a symmetric matrix, you can always rotate your coordinate system so that matrix is diagonal. This new axis, these are called the principal axis. This new rotated coordinate system is called, is called the principal axis. Instead of having a coordinate system like this, x, y, z, we're going to rotate it somehow like this. And in this frame here, this will be diagonal. You can always do that. That's always possible. We're going to call this new axis here that's rotated with that diagonal. We're going to call these the principal axes. If I draw a little cartoon picture of this, I can do this. It's X, Y, Z. Here's my chi. I have all this stuff here, chi XX, chi XY, chi XZ. That mess. I'm going to rotate my axes to maybe this. A little. Here's my new coordinate system here. And now when I write the chi for this, a little prime on it, meaning it's chi in this new frame. This is now going to become chi XX, 0, 0, chi YY, 0, 0, 0, chi ZZ. And these don't have to be the same. Okay?
What doesn't have to be the same?
These values here do not have to be the same. And they won't be the same. Okay? So these are the principal axes. We'll be doing that quite a bit in class. Okay. Yep.
And then we also have to rotate all the other matrix.
You have to, everything gets rotated. Okay. Yeah. And there's a way of doing that. We don't need that result. We're just going to say, we're going to work in this new axes like this. Okay. Why we're going to work in this as opposed to this? The only one reason. It's easier. This is a whole lot easier to work with than this right there. Okay. That's what we're going to do. Okay. So with that said, we can now start. I know I kept you here to 5 o'clock almost. Okay, so we'll go to old now. We'll have wings and beer. Yes, it seems like we all just started. Okay. Actually, what time is it? 3:55. Tons of time. Okay, let's start. Proceeding. So now let's drive the wave equation for an anisotropic crystal. So let's draw the wave equation. And actually, we're going to get the dispersion relation for an anisotropic. And you are pros at this, and you tell me where to start. Okay.
Trying to vector identity.
Which is what?
Curl.
Correct. There's a reason why we keep on using that vector identity. You have no idea what to do with this stuff. You start with that vector identity. You're probably, even if you don't know what to do, just starting with that vector identity, people think you're smart. Because they're probably not going to know it. They're going to think, wow, they're starting with that vector identity. They must be smart. Look how far I got. It's just, it's incredible.
So that means that in the physics community, if you set the curl of something equal to 0, then might think you're smart.
Turns out no one will. Okay, so what do we do with that? So we start with the curl of E equals. Okay, what is it again?
Gradient of divergence minus the flash.
Now, what we're going to do, we're going to assume a formable wave. Okay, we're going to assume a plane wave. Actually, before we do that, let's beat on this a little bit more. Sorry. Okay. What do we do with this again?
Minus partial of the
Good. And what do we do with the time of the curl? We switch them. What do we do with this?
mu naught J.
The mu naught J.
Mu naught epsilon
Mu naught epsilon naught.
partial of your expectation.
Which of you with respect to T?
I'm assuming we're not assuming the rho free is
We're gonna, something new is gonna happen. Like, can't wait to find out what. None of this is one bit obvious. I mean, this part is. not the other part. Okay, equals this guy here. Now let's beat on this a little bit more. Now, what do we know about J? J is made up of what terms?
Yeah,
J free, the JM,
G bounds.
and J bound. Okay. For crystal, which ones are we going to keep? Or which one?
G bounds.
Yeah, we're going to worry about free particles?
Yep.
No, we're not in the metal oscillator B stuff. We're going to worry about magnetic properties?
Yep.
Sign up. So now we have JB. We're going to call JB. Okay. What do we know about JB? Partial of your rho here is P. Your polarization vector is vector T. Make sense? So we put this all in here. What do we get? We get minus mu naught partial with respect to T. Okay, acting on this guy here. And so this will give me a second derivative here of this P. Right? That makes sense? Is this time derivative? Is that again that time derivative? Minus, okay, how do I write mu naught over epsilon naught? Actually, I'm going to leave it like that for a little while. Or do I want to get rid of it? I think I want to write it as one of C squared. I might regret that, but those things happen. Okay. This term. What do you do? And what do we know about this P here? This P is going to be epsilon naught chi x. I'm going to call chi xx just chi x. Is that okay? Do the same. In other words, this P here, or chi, is chi xx, and this is going to call chi x 0, 0, 0. Chi y. This is just anything chi y 0, 0, 0. Chi z z. So what is this going to become? X I hat plus epsilon naught chi y ey j hat plus epsilon. This is going to hurt. This is going to be a quest of a derivation. Okay. I wish we actually started the class here, but we didn't. This other stuff. But this is going to hurt. Okay. Epsilon naught chi z z. So that goes in for here. Okay. Now we will assume a traveling wave solution. I'm going to say that this E is going to be E naught, E to the I, K dot R, minus omega T. Make sense? Okay, this is going to hurt. Let's start. Yep. Oh. I think I'm okay with that. Yep. That minus sign is here. So if I take this and put it in here, all the terms have an epsilon naught, right? You can pull the epsilon naught out here with that. If I take a time derivative on EX, EY, and EZ, in other words, what is my EX here? What is EX here? Where's my X component coming in? The E naught part here. That's where the X component is coming in. Or this E naught here. E naught X if I have. E naught Y J hat. Uh-oh. That's E naught Z. So the C naught X is E naught X. E to the I. K dot R. And likewise for the EY. If I take 2 time derivatives of that, what do I get? Every time I'm going to pull down a minus I omega. I'm going to do it twice. This is going to give me minus omega squared e naught x e to the I here. And this guy here is nothing but ex. So this is going to be giving me minus omega squared ex. Make sense? And likewise for all the other terms. So if I put this in here, I'm going to pull out all the minus omega naughts, epsilon naughts here. I will then have, well, I have chi x. One other thing. All the terms will have a what? A minus omega squared, right? I can factor that out as well. If I factor that out, that'll make this term here positive then. So then what am I left with? I'm left with chi x ex plus chi y ey plus chi z ez, right? That's this term here. Does that make sense? What does this term here become? That makes sense? If I take a time derivative of this fellow here, all it does is put on a minus I omega once. I take another one, it does it twice. So get a minus omega, so with this guy here. I get minus omega squared. So I take that and put it in for here. I get plus omega squared over c squared. Okay. Equals. Let's hold off on this guy here. Well, actually, let's go do part of it. This one you worked out for a daily homework assignment. What did that one give you? From daily homework. I don't remember the number.
Oh, no, we got it.
What you guys equal? You all got it correct. I A not B. Y.
I mean, I think what we did, we proved that that was equal to I.
Yeah, how do we get?
Is it because when you break up the gradient operator and you take the derivative position?
Let's make sure we understand where that's coming from. When I have a gradient like this, and then the divergence. What does this equal? It's usually 0.
Partial.
The x is effect, sample, y. Okay, so where is the x dependence in? GR. You know what the k dot r? It's ex, I mean it's kxx, it's kyy, it's kzz. Right? So if you take a derivative of this with respect to x, what is it going to do? It's going to put down an ikx. When you do this guy here, this pulls down an ikx, and you still get the ex left. And this guy here gives you the iky, y, this ikz. Make sense? Which is nothing but my I. Yeah. Now, what is this guy going to do? These guys are gone. Okay, so now that leaves this guy here. what is that going to become?
Second part.
With that. What's that gonna be? We're gonna- This stuff again.
Second part.
Just kind of guess.
Same thing squared.
Minus K squared.
This is going to become minus k squared. Oh, yell at me one thing here. I got something here. This is going to be the case. And then we have this guy here. And what did we say this is? Epsilon naught kx ex I hat plus. Okay, so there should have been, there needs to be an I hat here, a j hat here. I apologize. So what do you think we're going to do next time? I'm going to take this term here and this term here and take them all the way over to this side here. I'm going to collect all the I hats together, all the Y hats, J hats together, and all the Z hats together. And then we have to figure out what this is going to be here. And what I'll do is I'm just going to give you the answer now and I'll prove it tomorrow. This is going to become minus k, k. Okay. Here's level one. Okay. I told you this is a quest. Yeah, but the reason why we're using this one here, this is easily the best development I've seen. Mostly they'll just state some facts and go, huh? And this is the only source I've come across where all the details are worked out. Okay. You have to be patient with this. Okay. So
Very patient.
have a good day.